Hello, I'm Delia Tabatabai, a computer science master's student from Oregon State University advised by Professor Min-Suk Kang. In this video, I'm going to talk about our paper titled Why Did My AI Agent Lose? Visual Analytics for Scaling Up After Action Review. AI systems often make errors in their decision-making process. Analyzing, finding, and resolving these errors is challenging. Such analysis for reinforcement learning agents brings additional challenges due to their complex, long sequential decision-making process and their particularity to specific domains. Thus, these analyses can be better performed by application domain experts who know the domain well, but they often do not have expertise in the underlying AI algorithms. Although most visualization tools for AI interpretability consist of many views and their users are often asked to freely explore them, the free-form exploration may not be optimal for these domain experts who do not know every detail of the underlying AI systems. Our team recently developed a new structured process for domain experts to assess AI called After Action Review for AI or R5. In this process, a human takes a series of steps to assess an AI agent and answers to questions like what was supposed to happen at the specific decision point, what actually happened at that decision, and why it happened. These steps can be repeated for all the decisions made by the AI. Let me give you an example of how R5 can be used for analyzing AI agents. Our team built a custom real-time strategy game using StarCraft 2. In this game, two AI agents, namely friendly AI on the left and enemy AI on the right, battle each other in the top and bottom lanes like tug-of-war. The friendly AI's action is determined by a reinforcement learning agent which predicts the best possible action to take every 30 seconds throughout the game. For example, it decides to purchase one of the three types of troops like Marine and place it in the top lane. The two players pursue the same goal to win the game by destroying one of the opponent's two nexuses, which you see at the end of each lane. But what if our friendly AI agent loses? We need to analyze this loss. The R5 process allows domain experts to perform structured analysis of a decision an AI agent has made. For example, for one of the AI's decisions, a user is first asked to predict what was supposed to happen using the R5 form shown in the video. And then they watch the game to see what actually happened and reason why it happened by answering a series of questions. This helps build the mental models about AI's reasoning process. However, the R5 prototype used in our previous study was not designed to scale to complex, large-scale, real-world environments. It was used to analyze pre-selected decisions that were known to have issues or bugs. In reality, a user often needs to determine which decisions to analyze, so the goal of this paper is to scale up the R5 process. We designed and developed a new visual analytics tool that integrates the R5 process for domain experts to gain the best insight into the agent's faults. Specifically, we augment the R5 process to be performed at three levels of granularity: episode level, decision level, and explanation level, such that users first explore the entire episode level, then determine which decisions to analyze, and then dive into detailed analysis of individual decisions with explanations. I will show you how our tool supports the three-level R5 process using the StarCraft domain I introduced earlier. In this particular game episode, as you see, the friendly AI lost because its bottom nexus has been destroyed. So suppose a domain knowledgeable user, Jane, wants to analyze why the friendly AI agent lost in this game. First, Jane was guided to perform episode-level analysis by answering three questions listed on the first R5 form, which works with the timeline view. It helps Jane get an overview of the whole game episode with a few charts. For example, Jane can identify that our agent lost this game because its bottom nexus lost all of its health points. She can see there was a turning point where things went downhill. In this case, it was decision 13. From other charts, she also found that the enemy builds a significant advantage starting at decision 11. So that's interesting. It makes sense that this forced advantage could lead to the health loss that starts at 13. Jane can fill out the R5 form on this. Now she got a hint that there might be something interesting happened around decision 11, so she can take a focused look there, which we call decision level analysis. She is guided to develop mental models through two steps: prediction and description. First, prior to a particular decision point, Jane examines the game board and is prompted by the R5 prediction form to put themselves in the position of the agent and decide what to do next. Then she watches to see what the agent actually did and enters that into the R5 description form. Here, the agent made a move in the top lane which was not expected. Jane can use the R5 form to make value judgments about what the agent did, connecting this action into thoughts about strategy. At this point, she is likely still curious about why it happened. Our tool helps her gain insights into the agent's thinking by using the explanation tree for each decision. It visualizes the AI's reasoning process as a look-ahead tree. The leftmost node is the root of the tree, representing the current state. You can think of it as a thumbnail of the game screen. And this state node has multiple children, each corresponding to an action the friendly AI can take and future states predicted by AI. For example, the first line shows that if friendly AI makes 4 marines at the top lane, AI predicted that there is a 99% chance of winning at the end of the game. Because AI thought enemy AI will make an immortal unit at bottom, next state will be like this after 30 seconds and so on. By navigating the tree, here the child information can be expanded. Jane can further inspect how AI made that decision and find any issues or bugs in their reasoning. For example, in this explanation for decision 13, she found the first two actions very suspicious. One shows near certainty of a win and the next shows near certainty of a loss, though their actions are very similar. And she can answer the why questions based on their domain knowledge, which can be forwarded to engineers who can potentially fix the problem based on their knowledge in AI. In summary, we developed a structured process for assessing AI agents which we call R5 and demonstrated how a visual analytics tool that integrates R5 can help domain experts perform analysis at multiple different levels. This can help build their mental models of the AI reasoning process, find issues, and systematically reason about them. In the end, I would like to thank DARPA for supporting our work. Thank you for your attention.